Okay, the second generalization that we want to make is when we have terms in our transfer function that look like s plus a to the n. So in this case, a would be an nth order pole or zero depending on whether the term is in the numerator or denominator, whether n is positive or negative. So somewhere within our transfer function, we're going to have a number of terms like this. And you can have more than one. You can have terms with different a's. So if we follow our procedure of substituting j omega for s and then putting this in Bode function form for the case of n equals 1, then you basically have the following expression. If we now take 20 times the log of the magnitude of h, we're going to get two extremes. In the one case where omega is much, much greater than a, we can ignore the 1. The magnitude of j omega becomes omega, so we would have omega over a times a, giving us just 20 times the log of omega. So that applies for omega much greater than a. For omega much less than a, basically omega over a becomes a very small term, which we can ignore compared to 1, and we just have 20 times the log of a, which is a constant. So the graph is going to be a constant for frequencies below a, and have a slope for frequencies above a. Now it's not hard to come back to the beginning and see that if this were raised to the power n, that we would have a power n here, which when we take the logarithm would come out front and multiply the logarithm, so our slope would be 20n dB per decade. So that's for terms that are of this type. So let's now go to MATLAB and look at some examples. So this is our previous figure. I'm going to go ahead before I close this out and copy this figure to the clipboard. And now I'll close this figure out and let's clear all. And for now we will hold off on the graph so that we don't retain any previous graph information. And now what I want to do is let's start out with terms where we have in the numerator some s plus a, and let's just let a equal 10. So if the numerator is s plus 10, then that would just be a 1 coefficient for s and a 10 for the constant. And the denominator will just for now have be 1. So now let's just show you what that transfer function would look like. And so this is our s plus 10. So now let's do a Bode plot of that. So let me come and be sure I get the right syntax. And now we will hold on to this plot. And so we're actually getting both the phase and magnitude plot. For now, I just want to look at the magnitude plot, which is the one on the top. This graph is going to range from 1/10 of a radian per second to 100 radians per second. You can see right here at 10 radians per second, we clearly have a transition that's occurred around 10. So we're starting at a 20 dB magnitude. That is an asymptote that runs up to 10 radians per second. And then we would have an asymptote that would run alongside the positively sloping 20 dB per decade. So this is the magnitude of the transfer function as a function of frequency. Notice right here at the cutoff frequency, we're basically up 3 dB. So there's a 3 dB for a single order polar zero. There's a 3 dB either increase or decrease in the magnitude right at the cutoff. In fact, that is the definition of the cutoff. So this would be a first order. Now I just want to make one comment here. that you wouldn't want this in a system. This is not a filter. It's not acting to cut anything off. In fact, what it's doing is it's flat at the lower frequencies and then it's amplifying the higher frequencies basically by a factor of 10 each order of magnitude. So you're getting a 20 dB per decade increase in the output as frequency goes up. So this would be a system that basically amplified your noise, and the higher frequency the noise, the greater the amplification rates. This is probably not something you would want in any kind of a design. So let's, but it's a legitimate function, and we wanted to do its Bodie plot. Let's now see what happens if you have s plus 10 squared in the numerator. So what we'll do is we'll do a second numerator, and in this case we will convolve the numerator with itself so that we effectively square it, and there's our coefficients. And so now let's hold on. Oh, I already did that. So now let's look at the Bodie plot of numerator 2 denominator. So our denominator is still 1 here. And so you can see what happens. The red line here in the graph, oh, and I need to adjust the gain. So let me do that just to, well, let me not do that. So this just has a different gain because I made it squared and it changed what the low frequency gain looked like. So if you'll bear with me through that, what I want you to note is that the slope here is significantly steeper. In fact, let me go back and let me give this a denominator of 10. And then that'll give them both the same gain. So let me hold off and let me do Bodie of numerator denominator again. Now let me hold on and let me do Bodie of numerator 2 denominator 2. Okay, and now I'm going to get what I want to see here. So I adjusted the gain so that they have the same low frequency gain, and I'll show you how I did that. But the point I want to make is this is your first order, your s plus 10. This is your s plus 10 squared, and you see the slope in this change region is much steeper. Now, what I want you to do is I want you to visualize a line here at 3 dB, which is our cutoff for our first order filter. Notice that our first order system. Notice that the second order system, the distance between the DC gain down here and the shift that occurs at cutoff is twice what it was with that first order. So increasing the order of the polar zero and making the slope steeper is actually going to move the curve away from the asymptote right at the cutoff frequency. Notice also in the phase shift we have twice the phase shift, and as I said, we'll discuss the phase shift later. So now let's come back and let's figure out what we would do if this were in the denominator of the transfer function. So let's make our numerator now equal to 10 and our denominator equal to s plus 10, so that would be a 110. Hopefully this is going to give me the gain that I want. Oops, sorry, used the wrong brackets. So denominator is square bracket 1 space 10. And now let's do the transfer function so that you can look at it. So So there's what the transfer function is going to look like. Let me look and see. That should be, I think, in order to get that to give me the correct gain so that they're all centered around the same place, I need the numerator to be 100. That should fix it. Okay, so now let's do a Bode of numerator denominator. Okay, and now you can see the difference. Okay, when the s plus 10 is in the denominator, as shown here in the transfer function, we still get the transition at 10, but now the transition is a downward transition, and the yellow line is actually representing a low pass filter. So this is one of the reasons when we talked about Laplace systems in general and transfer functions, we said that you're always going to want your denominator to be of higher order than your numerator. Otherwise, the system tends to become unstable. And you can see that illustrated here, that when I have an s in the numerator and nothing in the denominator except for a constant, I'm getting this amplification at high frequencies. When the s is in the denominator, making it a pole instead of a zero, you now see that I'm getting that behavior that's actually cutting off higher frequencies and leveling out at a constant at the lower frequencies. So let's do one more thing. Let's increase our numerator by an order of magnitude so that we keep our gain the same. And let's make our denominator s plus 10 squared. So we will convolve denominator with denominator, and let me make this denominator 2. Okay, and this should work. Let's, whoops, need a V. Okay, now let's look at what our transfer function looks like. You can always do that just to make sure that you didn't do something silly. Okay, so there's my transfer function. I think it's as it should be. So now let's do a Bode plot of numerator and denominator 2. Okay, and there we go. So you see the purple line is acting to provide a steeper slope in this band. I could go a step further, and I think I will. Let's make the numerator 10,000. I think that'll set my gain correctly. And then let's make the denominator, I'll call it denominator 3. We'll make it third order. So we will convolve our original denominator with our second order. Yeah, and then let's do a Bode of numerator and denominator 3. And so you can see this green line here is going to represent that. So now if I come to my omega equals 10, which is my cutoff frequency, you can see that each time I increase the order of that pole in the denominator, my actual value, because remember this curved line represents the actual value, my actual value continues to drop below the asymptote. So my question for you is the purple line and the green line, is that still the cutoff frequency for the second and third order low pass filter? And the answer is no, because the cutoff frequency by definition is the point where the order of magnitude of the transfer function is equal to 3 dB down. Let's see if I can expand this a little bit. Okay, so if you were to take a straight line here, right here you can see your 3 dB point is about right there. So to get the cutoff of the second order filter, I'm going to have to draw a horizontal line. And you can see that bumps back quite a lot. And the third order filter is bumping back quite a lot more. So just kind of eyeballing it, that's about, let's see, This is 1, 2, 3, 4. That's about 4.5 radians per second compared to 10. So we are less than half of our desired, if 10 were our desired cutoff frequency, we're at less than half of our desired cutoff frequency with that third order filter. So this just shows you, some of the things that happen when you do a Bode plot of this particular kind of term. So once again, just to review, the term that we're looking at are terms like s plus a to the n. The ones that we actually plotted on our MATLAB graph, we plotted n equals 2, n equals 1, n equals -1, n equals -2, and n equals -3.